The time is 2 o'clock in Gothenburg, Sweden, a sunny and cold end of summer, beginning of autumn day. And I would like to welcome you all to the final session of panel 4 about technology, processes and systems. My name is Simon Harvey. I'm a professor energy technology at Chalmers University of Technology. And my co-host of this panel, co-chair of this panel, has been Dr. Anna Realini from Research in Energy Systems in Italy. So let's see what we have going for us today. So this is the final session, and we were looking into excess heat today. And we have just 3 papers. You can see there. So we have one paper by Pontus Bokinge from CIT Industrial Energy, and he will be talking about the interplay between process decarbonisation and many of the technical options for achieving that, and how that affects excess heat delivery from industrial process plants and ways to tackle that in modelling exercises. We will go on thereafter to Max Biermann. He's one of my colleagues at Chalmers Energy Technology, in fact, and he will also be talking about excess heat, and he'll be talking about the interplay between using it for carbon capture or for district heating, and that's often that type of competition for excess heat is something which is definitely interesting to look into. So Max will be updating us about his findings there. And finally, we'll go on to a little more of a top-down study. We'll have Aydemir from Fraunhofer in Germany, and he'll be talking about these new ways and new methods for assessing realistic potential and cost for using excess heat for district heating, and he's tried to do that at the top-down EU 28 level. With some new methodology, with network analysis, which he will explain to us. So that's the program for this session. As usual, we will invite the speakers to deliver their material first, so without time for Q&A between the presentations, we will take the quick Q&A at the end of the session. And as usual, you're used to this by now. You have Hoover or you have Zoom. Please use the Q&A function and write down your questions and thoughts and comments on the fly, and we will handle them all at the end of this session. So I think that's it for the introduction. And now I'm very happy to hand over to Pontus Bokinge, who will talk, as we said, about process decarbonisation, how that affects targets for excess heat delivery from industrial process plants. So I now hand over to Pontus. I think it's a recorded Pontus.
My presentation entitled Effects of Process Decarbonisation on Future Targets for Excess Heat Delivery from an Industrial Process Plant. My name is Pontus Bokinge, and I work as a consultant at CIT Industriell Energi, a subsidiary of Chalmers Industrial Technology, specializing in energy systems analysis. The use of excess heat from industrial processes can contribute to societal targets for greenhouse gas reductions and energy efficiency. For example, several studies indicate that the technical potential for excess heat delivery from industry in the European Union is about 300 terawatt-hours per year, an amount that would be enough to replace more than 15% of the fossil energy demand in residential heating sector, which accounts for more than 1/5 of the primary energy consumption in the European Union. However, excess heat potentials are often based on data from current industrial processes, and it is uncertain how potentials will change in the future due to upcoming drastic changes of industrial processes. Specifically, decarbonisation of the industrial sector is required to reach climate targets for 2050, and will require a combination of measures, including a transition to bio-based and recycled feedstock and fuels, carbon capture and storage or utilization, and electrification. Such profound changes of industrial processes and energy systems are likely to affect the availability of excess heat. and a better understanding of how the excess heat potentials might change is needed in order to utilize excess heat in ways that can be resource efficient in the long term. Today, I will present a systematic approach that can be used to analyze how different decarbonization options may affect the potential future availability of excess heat at a specific plant site. The approach is based on the use of a consistent methodology for excess heat assessment, which is applied both to the current and the potential decarbonized process. The approach adopted in this work is to theoretically determine the unavoidable excess heat, which refers to excess heat that cannot be avoided by improved internal heat recovery or utilization. For the excess heat assessment, this means that the internal heat recovery and utilization is prioritized over excess heat delivery, and the following prioritization order is used. On-site combustion of any non-marketable fuel byproducts or waste is considered unavoidable, but after this, the first priority is to maximize internal heat recovery in order to minimize the demand of external heating and cooling, which corresponds to minimizing the demand for external fuels. The available excess heat after ideal internal heat recovery corresponds to the minimum cooling demand of the process and can be visualized by the process grand composite curve. This curve is a common tool in pinch analysis, and its construction requires information about the temperature level and load of all heating and cooling demands of a process. Is a graphical representation of the net heat flow characteristics of a process versus its temperature. In simple terms, moving in the positive x direction when going from a higher to a lower temperature indicates a heat surplus in the temperature interval, while moving in the negative x direction indicates a heat deficit. In the process represented by the curve on this slide, heat is available at high temperatures from combustion and cooling of flue gases, while there are significant process steam demands at lower temperatures. The minimum heating and cooling demand of the process can be read as the distance between the top of the curve and the y-axis, while the minimum cooling demand can be read as the distance between the bottom of the curve and the y-axis. In this case, there is no external heating demand after ideal heat integration, while the total cooling demand is 240 megawatts. This excess heat could be made available for export from the plant. However, heat sources available at high temperatures, as in this case, offer excellent opportunity for cogeneration of heat and power using a steam cycle. And the next priority in the excess heat assessment is to maximize cogeneration of power in steam turbines, as is illustrated by the dashed blue line. Here, high temperature heat sources are used to raise steam, and back pressure turbine extractions are dimensioned to cover process heating demands. If more excess heat is available after meeting internal heat demands, condensing power generation is maximized by increasing the size of the steam cycle and adding a condensing turbine stage. In the example on this slide, 100 megawatt of excess heat can be converted to power, reducing the excess heat availability to 140 megawatts. At this point, any remaining heat from process cooling or cooling of the steam cycle, as indicated by the red circle, is considered unavoidable and available for export. To illustrate this heat more clearly, a tool called the excess heat temperature signature was used in this work. This signature illustrates the amount of excess heat available according to predefined temperature ranges and constant temperature levels that represent relevant excess heat utilization options. Given the prioritization order used in the excess heat assessment, the excess heat temperature signature represents the theoretical maximum amount of heat that can be made available without limiting the potential for further primary energy savings or on-site power generation, and thus represents a measure of unavoidable excess heat. By comparing the excess heat signature of an existing process to that of a potential future process, an indication of how excess heat availability may change can be obtained. It should be noted that this approach is highly theoretical. For example, ideal heat recovery is assumed without accounting for the design of the heat recovery network of the existing process. On the other hand, the design is generally not known for the future process, and by making theoretical assumptions, a consistent approach can be used for both processes. The theoretical assumptions mean that the actual excess heat targets are likely underestimated, but the use of the consistent assumptions mean that a good idea about the change in excess heat levels can be obtained. The proposed approach has been used in several case studies looking at different decarbonization options. 2 case studies will be presented here. The first case study investigated the impact that a potential feedstock switch to biomass in the petrochemical industry would have on excess heat targets. Specifically, production of the light olefins, ethylene and propylene was analyzed, and production at an existing steam cracker plant was compared to a potential biomass-based setup producing the same quantity of olefins via methanol and ethanol. The required alcohols are assumed to be produced on site from biomass using a fermentation-based process for ethanol and a process based on oxygen-blown gasification for methanol. The second case study investigated the implementation of bioenergy carbon capture and storage at a Swedish pulp mill. In this case study, it was assumed that 90% of the mill's CO2 emissions were to be captured using MEA-based post-combustion technology. Beginning with case study 1, this slide illustrates the ground composite curve of the existing steam cracker to the left and the curve of the potential biomass-based olefins process to the right. Even though the same products are produced by both processes, the heat flow changes significantly. Excess heat availability at high temperatures is significantly higher in the bio-based process due to increased generation of combustible byproducts, and this is enough to more than compensate for increased process heat demands at lower temperatures. The change in process heat flow affects the integration of steam cycles, illustrated by dashed blue lines, and the power generation target is more than 40% higher for the biomass-based process. Unavoidable excess heat is indicated in the figure by red circles and will be highlighted on the next slide by the excess heat temperature signature. The excess heat signatures of the steam cracker and the biomass-based process are displayed to the right on this slide. The solid line indicating the existing process and the dashed line indicating the potential biomass-based process. As can be seen, total amounts of excess heat are roughly unaffected by the conversion to the biomass-based process, while excess heat temperatures are expected to increase significantly, and there is a more than 7-fold increase in excess heat above 85 degrees. Regarding the overall energy balance, it should be noted that the biomass-based process has a higher power consumption, and despite the increased power generation target, required power imports are expected to increase significantly. Moving on to case study 2, this slide illustrates the GCCs of the existing pulp process on the left and the process after integration of a carbon capture plant to the right. In the existing process, the process-related combustion of black liquor could theoretically cover the entire heat demand of the process, and there is no demand for imported fuels. High-temperature heat from this combustion can also be used for combined heat and power generation, as is illustrated by the dashed blue line, and a significant amount of power, 100 megawatts, can be produced. If carbon capture is applied to the CO2 emissions of the pulp process, as is illustrated by the right-hand figure on this slide, a significant heating and cooling demand is added, and the available high-temperature heat is not enough to cover the additional heat demand of the carbon capture process, meaning that external fuel must be used. According to the prioritization order, this work minimized fuel consumption was prioritized over cogeneration, meaning that there is no power generation in this scenario. This way, only a small heat demand must be covered by external fuels. Unavoidable excess heat is once again indicated by red circles here and will be highlighted on the next slide by the excess heat temperature signature. The excess heat signatures of the pulp mill with and without carbon capture are displayed to the right on this slide, the solid line indicating the existing process and the dashed line indicating the process with carbon capture. As can be seen, the total amount of excess heat increases significantly, although most of the increase is at very low temperatures. This increase is explained by the cooling demand of the carbon capture process. Regarding power consumption, the pulp mill's entire power generation is lost and the power demand increases by 20 megawatts due to the power demand of the capture process. Consequently, there is a 120 megawatt decrease in the power balance of the mill, which goes from being a net exporter to a net importer of power. To summarize, the theoretical analysis of excess heat availability indicates that both quantity and quality of excess heat will increase in both cases. However, the impact on the power balance is more significant, and in both cases, power imports increase significantly. Of course, more case studies are needed to draw general conclusions, both regarding the industrial sectors investigated in this work and industry in general. However, as indicated by this work, decarbonisation of industrial sites may significantly change potential excess heat availability and quality, as well as power generation targets. This makes it important to account for future process development when estimating the potential for using industrial excess heat in other sectors and applications. To allow more general conclusions, further work includes applying the systematic energy targeting to more case studies. The results could form the basis for further bottom-up assessments of sector-wide potentials for future availability of industrial excess heat. This work has already been started, and in addition to the case studies presented here, case studies have been conducted for decarbonisation options in the iron and steel industry and in the oil and gas refining sector. As can be expected by the heterogeneity of industrial processes and decarbonisation options, preliminary results indicate that the effects of decarbonisation on excess heat quantity and quality differs widely between different industrial sectors, but that significant changes, both upwards and downwards, will occur. And with that, I thank you for your attention and welcome any questions and comments.
Okay, well, thanks to the recorded Pontus for that excellent kickoff for this session. As we said, a reminder to those of you who joined us during the presentation that we will be handling Q&A at the end of the session, and please write your comments, thoughts, questions in the Q&A chat function, either in Zoom or in Hoover, depending on which platform you're using to follow today's session. Anyway, I think Pontus' second case study example was an excellent transition to our next presentation. Since Pontus was looking at the effects of integrating CCS or carbon capture at a pulp mill, and showed very clearly that that makes, at the end of the day, that is essentially in competition with direct export of excess heat, and a number of pulp mills do in fact export excess heat to district heating systems. But I think our next presentation by Max Biermann is going to look into that issue a little more in detail. And so with that introduction, I will hand the floor over to you, Max. So please go ahead.
Thank you, Simon. Yeah, I'm a PhD student at Chalmers Energy Technology, and I'm going to talk about CCS and district heating, as Simon said, and I'll focus on the capture process design and its operation. and the possible heat integration between CCS and district heating. So that is the topic of my talk. Let's see here. There's a slight delay. Okay, to start off, the current landscape is that industrial excess heat is often delivered to district heating, as we saw before in the presentation, together also with existing CHP plants which are intended to deliver heat. This is especially a Nordic perspective. And the future might hold that decarbonisation via CCS is an option, and then we will fight for a competition of heat, but there might also be heat integration options between these two processes. What is interesting then is that the character will change. We will not maybe call this excess heat anymore. Once we have to install a CCS plant, then maybe there's no excess heat left, basically. So this is a heat that has to be used for the process. So it's also a matter of definition, perhaps. I'm not going to go into those details though, but yeah, just as a side remark. The aim and scope of this work, which was conducted in the form of a master thesis this spring, was process industry that delivers excess heat to a district heating network, and the process industry should operate throughout the year. And the district heat demand is low during the summer, so there's a variability in how much heat is delivered actually to the district heating. And also we looked at heat as not being a main product, so it's not critical if you would remove heat to the district heating, if you would decrease the load. So we had two questions to be answered. One was to investigate into this heat integration potential. How much heat can be recovered from a CCS process if we put all the heat onto CCS, the temperature level at sufficient temperature levels to CCS, and see how much we can get back to the district heating system from the CCS process. And the second question is about CCS operation modes and the sizing of these plants from a techno-economic perspective. And there the question is, are we going to operate in varying load or in constant load? And I'll try to illustrate these two questions before I go into more detail what I mean with these. First of all, everybody I think thinks about CCS as a heat sink, and we see before that is of course the case. Here we have a process flow sheet for a typical amine absorption process, where we see that a flue gas containing CO2 is entering the process, is being absorbed in the absorber column here, and via a chemical solvent, so that CO2 enters into liquid phase and then is being released in the stripper again. Leaves via the top, water is condensed, and then the CO2 is compressed. So we see here in the reboiler, that's where the steam, where the heat comes into the process. And then we've marked up all the potential cooling sources, which of course could be, if the temperature level is sufficient, heating sources for district heating water. So that's what we mean with this. Is there a potential for heat integration? Just for clarification is what we're looking at. The next slide, I want to illustrate what I mean with seasonal varying load and constant load. We see here a graph saying that heat on the y-axis, on the x-axis, we have indicated with these nice figures the course of a year in terms of seasons. And here, if you imagine a process industry, for example, steel, cement, a refinery, running roughly at constant load throughout the year, there might be stops for maintenance, but otherwise the level of process excess heat is roughly constant. And then you plot against that how a district heating supply curve to the district heating network would look like. And if you do CCS, you have some options now. One option is to get rid of all the district heating supply, deliver no heat to district heating, and supply all this heat to CCS. So you scale, you define a plant size of this size. The second option is to build a plant of similar size, but maintain the amount of district heat supplied to the district heating network. So we keep on supplying, and due to this seasonal variation or variability in this load that is supplied to district heat, we create somehow a window of operation or increase the operation for CCS. So that means varying load for CCS operation. So during summer, when there is an excess of heat, the plant CCS is operating more intensely, and in the winter, it's operating on a minimum load. That's the second option. The third option is to build a smaller CCS plant than in option 2, and to keep operating under a constant load. Motivation for that is to lower the plant size and have a lower capex impact. The problem is then that you might need some energy, additional energy, to run the plant at this constant load when there is not enough heat. So these options I just wanted to illustrate before I will tell you more about or actually study. We did look at two different cases, a refinery and a steel mill. Noteworthy here is that we have different scales, and we also have different CO2 concentrations that affect the CO2 capture process. Then also the heat source is a bit different in character and temperature levels. We checked that they're sufficient for the CCS process. I think we assumed 125 degrees or 130 degrees, something like that. In the refinery case, we have process heat, so there's a heat collection network assumed, and in the steel mill, there's a waste gas-fired CHP plant that has a turbine bleed, which we can use for CCS. Important assumptions is that we only looked at the amount of heat that is delivered to the district heating, the max amount. That is the amount that we also consider for CCS. We did not look at any additional excess heat sources to limit our scope. And then here I listed some other important assumptions that we made, especially here the district heating temperature between 50 and 90 degrees Celsius. It's worth mentioning. Yeah, so results. The first question was how much heat can we recover from CCS and how much can be delivered back to the district heating system. For this, we looked at this sizing option 1, so maximize the plant size and send no heat to district heating, send all the excess heat from the process to CCS, and then see what would be left for district heating. We see this sheet again, and we identified, given a minimum temperature difference of 10 degrees Celsius for heat exchange, these process units here as most promising in terms of heat quality, that is temperature, and heat quantity. So here we see the stripper overhead condenser, and here we see the intercoolers in the compression stages. If we quickly look at some heat compositive curves, we can see here we plotted the temperature against heat, and we see this cooling demand in the CCS, which is basically a curve plotted over all these coolers that I showed before. And then you can fit in neatly this district heating curve between 50 and 90 degrees Celsius. And you see in the refinery case where we had 38 megawatts for CCS, that was the level of district heating supplied from that plant. If we would supply all that to CCS, we could recover 9.7 megawatts back. If we look at the steel mill, we have a different scale. Here, the curve looks very similar in its course, but it has slightly lower temperatures given the flue gas had been already cooled and was colder in general. Also there, we have a slightly different process configuration, which leads to some smaller modifications in these coolers. There is a noteworthy difference if we divide this amount of heat supplied to district heating from the CCS process and not normalize it to what is pushed into the reboiler as excess heat. Then we see that we have roughly 10% in the steel case and 25% in the refinery case. The key difference here is, I think, is the 10 degrees Celsius assumption as a minimum temperature difference. But other than that, it's the stripper top gas temperature, which is slightly lower here, and also the process configurations. We see also that there's a shift in pinch point. Okay, coming to answering the second question. The question was, are we going to operate our steel mill in a seasonally varying load or at a constant load if we want to maintain district heating supply, which means that we will have some kind of excess heat curve, depending on how you plot it, you have an excess of heat available for CCS during the summer. How do you size your plant? So we kept the delivery, and then we looked at what is possible. Here we have illustrated this again. We see seasonally varying load on the left side. We again plot the amount of heat available for CCS against the time. Here we see that the heat available for CCS in blue, and in red dashed we see the CCS reboiler duty, which follows this curve very neatly, unless or except for in the winter here, where the plant is required to run at a certain minimum load to be operatable. And this minimum load kind of is higher than what is available of process excess heat. That means you have to cover this pocket here with primary energy, which is in our case was natural gas, which we assumed. In constant load, you operated at a lower load here. So you have a larger heat deficit in the winter, and you have a heat surplus in the summer. If we plot the plant sizes, we see the difference here as well. So this is basically a ratio between CapEx and OpEx. And here the plant size is defined by the peak. Here the plant size is set to be the same CO2 avoided in emissions as in this one. So we're trying to achieve the same emission avoidance in both cases. I illustrate this here. This is maybe a bit hard to grasp. I don't know if you're familiar with these concepts of captured CO2 and captured and avoided CO2, pardon me. We basically have the same plots, only now we're plotting the amount of captured CO2. And in blue, we see the amount of CO2 avoided. And we require that these both plots, or both areas in both plots, are the same in size. And in red, we see the emissions from natural gas combustion, which is of course larger in the constant load case because the heat pockets are larger, where we have to supply heat, extra heat from externally. So here we can see that 99% of the captured CO2 is also avoided CO2. Here it's only 93% of the captured CO2 is also avoided CO2 because we have additional emissions. We have larger emissions here from natural gas consumption than here in the left case. Okay, I'll quickly show some economic results. Here, this is maybe a bit hard to follow, so bear with me. We see on the left-hand axis the annualized costs in euros per year. And on the other y-axis, we see specific costs in euros per ton CO2 avoided with these. So the bar plots is the annualized cost, and the purple dot here is the specific cost. And we see all these three cases now compared to each other for the steel case. And that the first case here is where we sent all the excess heat to CCS and there was no district heating delivery. What we see is we can have a quite large amount of CO2 avoided. We receive a specific cost of roughly 40 euros per ton CO2 avoided. What is interesting then, if we can maintain district heating in case M3 and M2 here, is that we achieved roughly the same specific cost, same order of magnitude. And the main reason for that is because you would expect a scaling effect, right? Because you have a lot more CO2 avoided here than in these two cases. You would expect these dots to be a lot higher. And the only reason why they're not higher is because you have a loss in revenue from district heating supply. Because here you're not able to supply your district heating anymore, and that is quite costly. So that is one takeaway of the slide, that the loss in revenue is quite substantial. And the second takeaway here is that the seasonal varying load operation here is also quite comparable. Is a bit higher, but is comparable to the constant load operation. And that is mainly, well, it has a larger capex, similar to, it has the same size as this M1 case, but it has a lower variable OpEx because here more natural gas is combusted. So this is of course just a snapshot or a view on these specific points. We've done some sensitivity analysis as well, and we've found that this is very dependent on several factors, which I will summarize now in the conclusion slides for you. Yeah. So what we can say from our study is that there is a recoverable amount of heat from CCS for district heating in the range of 10 to 25% of what you put into the reboiler. Well, of course, depends on all the assumptions, mainly on the minimum temperature difference on the stripper top gas temperature in the CCS process, and the process configuration of such process as well. We looked at the sizing issue and the CCS operation mode and found that the seasonal CCS operation with excess heat has comparable costs to constant load operation. And that what we found in our sensitivity analysis, which we're still conducting, is that this is very sensitive to, this finding is very sensitive to ratios in energy price and the scale of process industry, and the sizing of the CCS plant, how that is done in general, and the shape of the excess heat load curve, of course. So that's very interesting to dive in further. And we also found that seasonal operation, of course, uses less primary heat, which is interesting. And also because you oversize your plant once you build this, you have the possibility to, in the future, scale up your capture rate. So you can intensify capture operations later in time in case there should be any more released heat from further efficiency measures, or if there should be another alternative for supplying heat to the CCS capture plant, for example, via heat pumping or electric boilers or so, if renewable energies should be that cheap to allow such schemes. And the last point here is that this revenue loss from decreased delivery of district heat is very considerable. And for the process industry to move away from supplying district heat as they are doing now, that would have to motivate it, of course, via some emission regulations. So if you require that CCS is actually conducted, so make it mandatory like gas cleaning is today, or if you implement funding mechanisms that do the job. Yeah, thank you for listening. I've listed some relevant publications from our group on that topic, if you want to dive into this. Yeah, thanks.
Okay, great. Thanks a lot, Max. That was really interesting to listen to. Now we have the challenge for Ali, because we've heard now a couple of presentations which have been very much at the process or individual plant level, and some methodology and development there. And now you're going to show us, Ali, how to put that all together at the EU 28 level, which I guess is quite a challenge. So
hi, Simon. Yes.
Extrapolate from the plant level up to the EU 28 level. So the floor is yours. Please go ahead.
Yeah, hi, Simon. Thank you for the introduction. You got it right. So the presentation I'm going to give you is a bit more on a higher level. So I'm also maybe being a bit brief on some slides. Yeah, and I'm waiting for the slides right now. Carol, do we have already opened the slides? Oh, yeah, I will wait. Here. So I'm going to give you a presentation on, let's say, the estimation of potentials for, let's say, industrial excess heat utilization for district heating networks for the EU 28 on the basis of network analysis. The agenda of my presentation is on the next slide. So first, I will give a brief overview of the background, because I think the context is very important when presenting the method and also discussing results and conclusions. Afterwards, I will introduce you the network approach we choose and show you maybe some basic insights how this code we actually implemented in a web platform works. Afterwards, I will present some results and then proceed with the discussion and conclusion. And let's come directly to the background. As you all might know, heating is quite important with regard to decarbonizing the energy sector. So we have a lot of heating in industry, but also a lot of heating in private households for buildings. So if we look at the energy balances, then we will see around half of Europe's total energy needs is with regard to heating and cooling. And most of it is heating, basically. And is still very dependent on fossil fuels. And if we want to meet somehow the decarbonization goals, we have to move fast. There's rapid change required, because Within the heating sector, for example, you can just imagine, for example, for household appliances, you have a very fragmented sector with a lot of decision makers, and you can't solve it top down. So you need somehow a local perspective and local solutions. And within this context, you will find a lot of publications dealing with district heating, or let's say amplifying the role of district heating with regard to this decarbonization, especially within the context of the building sectors. So what you can already observe is that countries with a higher share of district heating, for example, the Scandinavian countries, they also utilize a higher share of renewable energies for heating and cooling, especially for buildings. So you see somehow a correlation. However, we don't know if it is a cause or effect, but this is very often at conferences a pro-argument for district heating with regard to decarbonize the building sector. And so this topic is very intensive discussed within, let's say, strategic heating and cooling planning. And when the topic of setting up new district heating networks is evaluated in many communities within the framework of strategic heating and cooling planning, very often the question is raised, are there any like cheap heat sources to let's say also strengthen or give pro arguments for setting up networks? And within that context, excess heating is mentioned very often. And this is the framework for the method and also the code, which is implemented in a web platform I will present you afterwards. So the work I'm presenting you is based on a EU-funded project. It's called Hot Maps. So I will give you an updated link in the chat afterwards. So Hot Maps is something like web-based interactive platform where you can find basic data on the heating sector, and you can do strategic heating and cooling planning with it. And the audience group or the user group intended to use these platforms are public authorities. And within this platform, there was also a demand to somehow give the public authorities an idea about what excess heat from industry might achieve within their communities, within their local areas. And what we then did is based on a standard data set, what we have to develop a methodology which is intended to do so. So we are calculating in the end prices to transport excess heat to potential district heating areas based on network analysis. And the method is basically implemented in two larger steps, I would say. The first step is very common. So within strategic heating and cooling planning, the first step is usually to find areas with favorable conditions for district heating, and this varies a bit between countries. A very common approach is just to filter cells on maps where you have a minimum threshold with regard to the heating demand. So the idea behind is the higher the heating demand is, the higher the potential for district heating is due to economies of scale. So that is the background. And we apply this methodology in our excess heat estimation. So what we are doing within this platform is based on the default data given there, we first extract all the raster cells with thresholds which is higher than 50 terajoule per kilometer square. So this is, I would say, a common value which, for example, has been used also in the heat roadmap Europe. And then the second step is, which is more novel, is we generate networks, and we have like I would call it like 5 intermediate, 5 smaller steps here, how we are doing this here. And I'm going to present you on the next 2 slides on a visual basis what we are doing there. If you see on the left side the map, which is a bit small, you will see that there are some red cells which should give you an idea of the cells with potential for district heating. And then you have some triangles. These triangles, for example, might be companies, and these companies might be excess heat. So we have data on excess heat, and the first task is to somehow connect these triangles to these areas. And what we are doing here in the first step is we are creating edges and nodes to connect all potential heat sinks and heat sources in the end. And then there is a methodology from operations research where you are trying to minimize distances in networks. So it's called deriving minimum spanning trees. And what we are doing there is we apply this method. You see it on the left side here to connect all heat sources and heat sinks in an indirect way in order to minimize distances, with the idea behind that we don't want to have too many pipes. So we are like trying to reduce investments necessary here for generating our networks. And then in the next step, 2C, we are calculating the load we can provide from the heat sources to the heat sinks. And as we have already seen in the presentation before, this always depends on the load profiles with regard to the excess heat sources we have, but as well with regard to the load profiles of district heating. I've chosen here a bit unusual profile for district heating. So in the summer, the profile is going up, only for visual expression. And what we are doing here is basically only calculating the intersection, and based on this, we are deriving the maximum capacity we can transport between the heat sources and heat sinks. And then in the last 2 steps, D and E, we are somehow optimizing the network. So based on the flows we calculated then between sources and sinks, we are sizing pipes, pumps, and heat exchangers. And then we are setting in the step E thresholds to optimize the network, but not with an optimization function as you usually know it from operations research. It's more heuristic. So we define a maximum threshold with regard to cost per pipe in cent per kilowatt hours. So and then we are the code is varying the network. So he's mutating the network so long until all pipes have specific costs which are below this threshold. And that gives us the possibility in the end to show up to which thresholds how much excess heat is being transported within our network. And here we have the purpose I introduced in the beginning reflected. We want to show the user, okay, how much excess heat in your area you might transport to district heating networks for which cost. So we have here a slide for the result. What we have done here is based on our standard data set. We did some sensitivity calculations. So in order to show, okay, within the whole data set, how much heat is being transported or is flowing through the network, up to which cost. And it's also differentiated by countries. And here for sure, we have some proxies. So there are some countries with high amounts of excess heat. So maybe our database is just having more data for these countries, but by tendency you also see, okay, the higher the country, the more industry you have the country, the more excess heat is being transported. With regard to some key values, we have seen, okay, up to 0.75 cent. So 1/4 of the heat is like 1/3 of the excess heat is transported within the data set. And then an interesting figure is so nearly half of the excess heat is flowing through the networks we have in the EU28 countries, is based on our, let's say, cost assumptions, around 1.5 cent per kilowatt hours. And what we also see, then we have like a decrease in transporting excess heat. And this is because in our model, we have defined some maximum distances. So there are some excess heat sources in the data set which are then cut in the way because they are too far away from possible sinks. But we also well have heat losses foreseen in the pipe dimension, and we don't optimize the pipe dimension, so we are not increasing the sizes. We are only using standard values from engineering tables. So if the heat losses are too high in the way that we lose too much heat, we also are cutting these pipes. So then let's come to the discussion and conclusion. So what I presented you is a feature we have in our hot maps toolbox, which is based on a heuristic to show communities potentials of using excess heat in their district heating networks or potential district heating networks. We are not using an optimization, we are using an heuristic with threshold values. What has to be always critically reflected within such analysis is we are using specific cost data from, I think, Swedish engineering handbooks, so Swedish experiences on district heating networks and corresponding costs. So we have somehow an uncertainty because it's very often unclear how good you can transfer cost data from other countries to other countries. What we also see within our standard data set, we don't have so much excess heat covered. So we have around 100 terawatt hours. And as we have also seen in the presentations before, other top-down estimations are a bit higher, so up to 3 or 4 times higher. Here we are using at least a bottom-up database for the plants. So we could increase this if we have more information for more plants. And what is still a weakness in the tool and what will or might be extended in further development is that up to now, we don't know or do not have a standard data set for a real distribution of excess district heating networks. So what I already mentioned before is the analysis is only based on potential district heating areas, so not real existing district heating areas. So yeah, this is a data question where we could extend the toolbox, but in the end, within the functionalities, the user also have the possibilities to include this information in their analysis. Yeah, and one key figure was, as I already presented before, that there's quite a large amount of excess heat in our analysis, which might be delivered to nearby, at least communities. So from our point of view, excess heat really might be a driver for setting up or at least extending district heating networks. And if we have some time, Carol, I'm not sure if I can use your browser. So I could just open the toolbox maybe also, or at least send the links in the chat, and you could try it out afterwards directly. So I think there's no browser. Okay, I will just send it to the chat.
I think it's a good idea if you just send it.
Yeah, because the link is not up to date. We moved it, some days ago because the toolbox is developed, decentralized. So we have several institutes working on it. And so, it's very hard to align the IT infrastructure and these calculation modules where, for example, our method is also implemented. They need to be revised from time to time with regard to, let's say, calculation time. And so we needed an update. And for all the interested users. You can check it out. It's open source, it's free. You can also download all source codes. You can find further information on the wiki on that. Yeah.
Okay.
Okay.
Thanks a lot.
Yeah, that was my presentation basically. Thank you for listening.
All right, great. Now I'd like to invite all of our speakers to turn their cameras back on, and we have some questions come in both through the chat and the Q&A, but let's see. We had one which was clarification to you, Ali. So let's see what happened to that one. Why don't we take that one straight away? That came through the chat. There's the chat. Yeah. Okay. Okay. Yes, this was a quick question to Ali. And that was, what cost was included in your cost thresholds, so 0.75 to 5 cents per kilowatt hour?
It's a cost threshold. Yeah, the methodology is like two-step based. When we set the threshold is only for the pipes. So you have the investments for the pipes. And I think we also assess pumps, but don't include all heat exchangers. And then we optimize the networks, but in the final cost calculation where you find the levelized cost of heat for the networks, we include all costs per network. So if you go to the tool, or if I go back to the pictures, I think on my title page, you have seen a picture like where some sources were connected with some things, all costs for pipes, pumps, heat exchangers are included, and also operational costs for the pumps. So we calculate very basically how much electricity with standard efficiencies you need to transport the water and so on. But yeah, it's very simple, so it's not like a high detailed technical model. I think the equations are also, or I'm pretty sure they're described in the paper, basically, yeah.
Okay.
And with regard to the second question, I mean, it was from Matthias. Maybe I can also answer directly whether we
directly, since you're on there. Yes.
Yeah, whether we, because I'm looking at it right now, whether we looked at different temperature levels of the excess heat. Yes, they're in the standard database which had been created within the project. You have like 3 temperature ranges for excess heat, but we only have one. We assume a standard delivery temperature for the district heating network. So
what's the value? Can you tell us?
So it's 100 degrees. So we set it standard to 100 degrees. So in the beginning, we also thought about making it more detailed, but somehow it's not so easy to define the level of detail you need for public authorities we are dealing with. Yeah? So you are dealing with climate managers, basically, from communities. So somehow you have to design the toolbox in the way that it's not oversimplifying, because also with regards to the cost, the major important thing for us is with regard to strategic heating planning is that they see the potentials for district heating area, so they can somehow identify areas where it might make sense to further or deepen analyze it. Also have a possibility to somehow plot the excess heat within their maps and somehow draw some connections and at least get an idea what might be cost for supporting. Yeah, what is the order of magnitude? Yeah, and then for sure, if you go more into detail, you need studies on, yeah, I would say on a higher level of detail. It's more with regard to conduct strategic heating and planning. Yeah, and yeah, in the toolbox you also can then calculate scenarios with regard to future development of the demand for heating, so you can combine it then. For example, you can, make 2030, 2050 analysis and check out, okay, what are the areas for district heating? Do I have still excess heat? They have the possibility to include their own plants and to work in a way iterative. It should be more like a, like a workbook for them. I would explain it like this.
Okay, thanks.
Yeah.
Thanks a lot. And maybe it's just something which the audience, some members of the audience maybe didn't pick up, but when you illustrated your methodology, you actually had a map, and that was the Gothenburg area, right? Yeah.
Yeah.
No.
Yeah.
I'm
Yeah,
not sure if you said that, but I'm saying
no,
that's the benefit of the audience. That was the
yeah.
Gothenburg area. Yeah.
Yeah, actually, I don't wanted to say it because we had no data on it. I've seen there are some plants within it, but we have no excess heat estimated because these are refineries. And within this project, I mean, as you know, offers are always somehow standardized, structured, and our duty was to deliver like excess heat estimations for industry sector and not refineries. And so there are no estimations for refineries right now. So you need to put that in, or the database need to be extended. I mean, that is for sure. Yeah, that is a task of the user, or maybe further project or revisions. But within the first project, we haven't done it. And the basic idea was also, I mean, you know the concept of TRL. So this toolbox has a TRL of 7. So the idea was to demonstrate something, to have something like a pilot, but it's not like final. So there are still some steps to do to optimize it.
Okay, well, thanks. Now let's leave you as answering questions and go over to the question you put to Pontus there in the chat. So let's have a look at that one. Pontus, question for you. So Ali wrote, if I look at the needs of the processes without utilities, then the GCC should always give me the theoretical minimum. Yeah, and I think you can answer that one, but I think that's
correct. Sure.
And then you had some follow-up questions there. So the methodology consists primarily in showing the effect of the integration of CHP options on the theoretical minimum, and a question about the practical experience of that, and how much of the potential savings can you in fact achieve in practice, and experience from Sweden. So you want to comment on those questions, Pontus?
Yeah, I can comment very briefly here. Sure, yeah. If you look at the process without utilities, the GCC should show you the theoretical minimum heating and cooling demand, so that's correct. And then to the other part, about how much of the potential savings from the sort of maximum energy recovery scenario that you can actually achieve in practice, I would say that's very case dependent, depending on obviously how energy efficient your process is to begin with, and also some economical considerations of the plant in question. So I wouldn't really want to give a number here. No, that's right. To say that's very case dependent.
Okay, thanks. Yeah, it's hard to get figures on that because it was interesting me how much when you do some pinch analysis and you go to the customer, so how much do they really implement? So what is, so the experience, but okay.
I can imagine that it's hard to get anyone to give
okay,
number for that. Yes.
Thanks.
And Pontus, and you maybe want to comment, because your assessments were done assuming a delta T min of 0, which is of course the ultimate theoretical potential, because it's in theory it means infinite investment costs. So how do you think, or what would happen if you tried to put more realistic delta T min in there? How would the method still be applicable? Or any thoughts about that? So maybe a more techno-economic potential estimation.
So the reason for that is to basically avoid making too many assumptions about the sort of future processes that we consider to be very consistent. We use very theoretical assumptions. So if you would increase that, then the absolute numbers, the absolute amount of excess heat would increase in these estimates, because you would recover less heat with a higher temperature difference. But the idea is that the difference between the existing process plants and these potential future process, that we still think that we capture that difference.
Trends, okay. I think Max had a question for you, Pontus, as well, and that he was interested in the capture target rate, which was set for the pulp mill BECCS case.
Yeah, so that was that's 90% of the emissions from the recovery boiler and the lime kiln, so not including the bark boiler.
Okay, and was there a reason for that you want to comment on?
For not including the bark boiler?
Yeah.
Yeah, sure. So in that very theoretical case, you don't need the bark boiler.
Okay, so there is no bark boiler. Okay,
Yeah.
That's a good reason for not including it then. Yeah, we'll approve that. Let me see. I think this was another question to you, since you're with us now, Pontus, from the audience. This is the one in the Q&A, so I'll read it up. Thanks for the interesting presentation. That's also important to underline. So the question was, in a multi-process plant such as an oil refinery, isn't it possible that the findings could change substantially if one was to consider more than one isolated process? That was the question which we got in the Q&A here.
Sorry for being quiet for a while. Had a bit of a mishap with the microphone. Can you hear me now?
Yes, we do.
Yeah. Okay, great. So to that question, I guess that might refer to the final slide that I showed, where we had looked at the hydrogen production unit of an oil refinery, and in that case we actually do consider the effect on the entire refinery. So we have a common steam system connecting the various process parts with each other, basically. So what we do in one of the processes affects the steam balance of the entire refinery, and we actually do take that into account. So we look at the effect on the steam balance of the entire refinery and not just on the hydrogen production unit.
Okay.
And also the fuel balance of the entire plant. Yeah.
Right. See, we had a question from Max here. So we had a question: could you quantify the relative additional energy input for CCS on top of the production process in your examples?
Yeah, I can try. I had to look up those numbers actually now in the report that I have about this, the thesis report. I don't have the numbers in reference to the production process, but I have it in reference to the excess heat. So in this case, I only have the steel case here. For the seasonal varying load, you would have an excess heat of 453 gigawatt hours per year, and you would need a natural gas roughly 25 gigawatt. So that's it's a factor of 20 basically. Mm-hmm. And the constant load, you would have 320 gigawatt hours per year in excess heat that you would normally supply, but in natural gas you would need 200 gigawatt hours per year. So there's a substantial difference in how much natural gas you need for this constant load case, where you have to provide extra heat to operate your CCS plant constantly instead of with varying operation. Yeah.
Okay. A question I can put to you, and this is going back to this delta T min issue, right? Mm-hmm. You showed you'd been matching composite curves essentially of the excess,
yes,
the heat being released by the carbon capture process and your district heating. In the steel mill case, you'd assumed 10 as a delta T min, and well, it was looked from the curves, from what I could see, as if that if you'd relax that constraint just a little, you would have been able to recover a lot more excess heat. You probably could have matched the curve pretty much the same way as in the other plant.
Yes, that is my...
just tolerating a delta T min of 8.2 or something, which at the end of the day wouldn't make much of a difference.
Yes, basically those curves are, I mean, basically you should maybe assume this delta T of 0 and then see what the actual differences are dependent on like a theoretical approach between those two curves, and then you would see a difference. But I guess you're right, they're probably pretty much the same. Then you would really lift up the differences due to flue gas concentrations and also process configurations of the CCS plant. That is correct. That is something we didn't do, but we should have done.
Because assuming a value is just based on experience, and normally that's more or less where we usually end up. That's the way practitioners go ahead. But of course, you always need to challenge that. But you can't do everything within a master's thesis time lapse.
No, but that would definitely have to be challenged for a paper which we're working on right now. So that is, we've gotten that comment already from Elin. So.
All right. Got it from me again.
Perfect. No,
another one is you're assuming compression to 7 bar in your compressor train. What happens if you went to 15, which is one of the other levels which has been considered for all of these CO2 transportation to hubs and so on? Would be a lot more heat released from the intercoolers there in the compressor train? Did you look at that?
We looked at that because the reason is the compressors don't go to 7 bars. The 7 bar is the actual output flow. So the compressors go already to 20 bars. So the compression is higher, and then you have some pressure release and some cooling and to modify the right. So the process there we derived from a different paper, from an already published paper from another research group. We checked this with our own model of compression, and we modified the compression stages, and we also, I think, checked for the pressures, but it didn't make much of a difference. The curves I showed was also, there was a high temperature. The highest temperature was in those intercoolers, but the amount of heat is so little because it's basically only the CO2 flow that is going out. So that flow is very, very small compared to all the other flows in the CCS process. So the largest amount of heat you can get in the condenser, where you have to condense out the water and the stripper. So this compression thing, we will probably look at more, but my guess is that it will not be so significant.
Okay. All right. I had something else for you or for someone else. What happened to that one? Yes, okay. That's the heat pumping I wondered a little bit about. That's to you as well, Max. If you were to throw some heat pumps in there, because it looks as if you still have quite a lot of heat there, which is at acceptable temperature levels. So if you were to boost that with heat pumps, is that something you've looked into or thinking about looking into?
We haven't looked into that, but we are going to look into that in a different project maybe. So I don't know if we're probably not gonna do it in this work, but I think that's definitely interesting. And what I've heard also from some real cases is that is an issue. Once you have a process that is connected to district heating and you implement CCS, as I think was the case for one of those Norwegian plants which are planning to do CCS in their feed studies, there you would you have the problem that you run out of heat if you want to supply excess heat to district heating or some heat. Then you have to do heat pumping, and they were looking at that. So I think that is a real option, actually.
Okay, neat, good, interesting. All right. But your take-home message is, I think, which is interesting for me and for others, is that of the heat which supposedly you lose, you can in fact recover 15-20%, and that's not bad. Yeah.
That's not bad. No.
With heat pumping, if you could maybe squeeze another 10 or 15%, even better.
Yeah, the key thing is not to destroy so much heat with other measures that you don't have enough to run the CCS. You need the right temperature levels. That is the key challenge. So any efficiency measures that you do on plant should be weighed against future CCS operations.
Yeah.
I think that's also important to consider.
Okay, well, thanks to all of our panelists. I can't see any more questions in the chat, and I don't see any more questions in the Q&A browser either. Anna, you're maybe on top of things which may be happening in Hoover. Is there anything else which has come through?
No questions in Hoover.
Okay, so everyone's been putting them here straight through Zoom. Great. Well, if that's the case, I think we can wrap up. Thanks to all of you. We've had some great presentations and some really good discussions. And thanks to all of the participants. So this was the final session for panel 4. So thanks from Anna and I. It's been a pleasure chairing these sessions. We've heard some great stuff. All right, so good afternoon to all of you, and hope you've enjoyed the conference, and particularly panel 4, of course. Yeah.
Thanks a lot.
Okay.
Thank
Bye.
you.
Bye, guys.
Bye-bye.
Bye.